So I'm going to turn the time over here to David. David is our lead tech support here at Isograph. He's been with the company 13 years. I think you'll find in short order how knowledgeable he is, and I think he'll make this really clear and simple for you. Please do not hesitate to jump in, chat, if you have a question. I mean, this is a really informal setting where, again, we're here to help you get started and understand what you're looking for today.
Okay, perfect. Will do.
It's all you, David. Thanks for your help today.
No problem. Hi there, Chad. Yeah, so thanks for the introduction there, guys. So, yeah, my intention today is just to show you around, I guess specifically, the AvSim or availability simulation part of our availability workbench software suite. This is the part of the software that would allow you to build block diagrams and analyze them to try and predict the availability and productivity of any kind of plant, just based on the reliability and maintenance data that you are able to provide. So by way of an introduction, reliability block diagrams, if you've not seen much of them before, it's basically a form of logic diagram that lets you represent the kind of reliability relationships that exist between your equipment. So for example, do you have a train of equipment where there are bottlenecks, a single failure bringing down the whole system? Are there redundancies where the system might only fail if 2 or 3 or more equipments were to go down at the same time? All of these kinds of relationships can be modeled using a reliability block diagram. Now, the way AvSim utilizes this is that you can build a block diagram that represents the relationships between your equipment. Then each of those blocks, representing maybe equipment failures and other things, you can populate with what you know about the failure and repair and maintenance of that particular equipment. So things like mean time to failure, if you have that information, mean time to repair, any scheduled maintenance tasks that are taking place. The program can then use Monte Carlo simulation to simulate the failure, repair, and maintenance of those equipments and how those various events are interacting through your block diagram to cause downtime in your system and losses of production, costs, and other things. So in AvSim, if you want to build a block diagram, the first thing you would do is tell the program, I want to add a new system. So this is going to represent whatever. Go ahead.
Real quick before you get into it, we do have, so what's interesting as you were talking through, if we have some of this information, so we do have mean time between failure. We are tracking it on all of our assets. So that's something that, is that like an input into the block diagram? If you know current MTBF? Okay.
Yeah, so if you know what the mean time to failure is for your assets, you can use that as information in the program. So I'll be able to show you how the diagram is built and what that represents, and then I'll show you about how you can enter that kind of information.
Okay, cool.
Yeah, we can create the system, so this might represent a system or a plant that you're modeling, and then using either the add menu or the toolbar, you can add blocks that represent maybe equipment or equipment failures in your system. So I can add a block and then just left click, just to add these blocks to the diagram. Then I can right click and go back to the regular cursor, and I can double click on these blocks and rename them. So that might be equipment 1, equipment 2, equipment 3, and so on. So the way the logic of a block diagram works is that a block diagram will always have a single input and a single output. And what we're looking for is a free path that will take us from the input to the output, and paths can be blocked by outages. So if a block is failed, then that blocks that path through the block diagram. If there are no paths available, that's when the system is considered to be out of service. So what we need to do is basically connect the blocks together in such a way that there is a single input and output, and the way they are connected together represents that kind of reliability relationship. So I need to connect these two blocks, and I'm going to connect them in parallel because that's what's going to give me a kind of redundancy relationship. Two blocks connected in parallel, that's two redundant equipments. So I'm going to need common input and output points for those connections. So I will use nodes for that. Let's add a node here and a node there maybe. And then I will just add some connections. So I click add connection, click where I want the connection to start, click where I want it to finish, and it connects those blocks together. So I can kind of connect everything together like that. So as far as the program is concerned, at all points during the simulation, it's keeping track. Can it get from here to here, basically? So, if one of these guys fails, you're still okay because you can go that way. But if they both fail, or if this one fails, then what you end up with is the path through the system is blocked, the system is out of service. It's worth remembering that the program is not modeling any kind of process or flow of product. This isn't intended to represent the actual way your system is connected together, although oftentimes it will look a lot like that. This just represents the logical relationship from a reliability perspective. In this case, it's very simple. Just parallel for redundancy, series for bottlenecks, for trains of equipment. And the program will let you go into a great deal more detail. So, for example, this block here might not be an equipment. It might actually be a subsystem that has its own internal structure as well. So I can select that block and I can page down inside it. I can say, okay, system 3 is actually a subsystem. We'll go inside that system and then we can add more equipment. So I might add more blocks in series or parallel, however I want to arrange them. Again, I can just connect them together. So now I'm inside system 3. I should also see here that system 3 has appeared as a kind of subsystem in this hierarchical view on the left. I can move between them that way. If I go back to my system level, you can see system 3 now has this icon next to it, which I can click on, and that takes me down to that system as well.
Okay.
So the program will not limit the size of your block diagram, and nor will it limit the number of layers of subsystems that you can go down to. I've only gone down one layer. You can go down as many as you want. Obviously, the speed of the analysis will be affected depending on the size and complexity of your model, but in principle, the program won't limit you on how big your model can be. So once you've built your model or your block diagram, then you would need to populate that with failure or repair and maintenance information. That's done through the failure models. So I will create a failure model. And this is where you can say to the program, okay, this represents the failure of a particular piece of equipment or a specific equipment failure mode. And on the failure tab, you can provide the program with that information, like, for example, mean time to failure. For more complex failure behavior, there are other distributions, things like, say, viable if you wanted to model wear out, or even tri-viable if you wanted to model like a bathtub curve for a piece of equipment. So you can see there's a variety of options available. You can also use historical failure data as part of your model as well. If you've been collecting times to failure or repair work orders for a piece of equipment, you can import that data into the integrated viable analysis tool and then use that information as part of your simulation. So essentially, your simulated failures should be following the same trend as you've been observing in your real system. And at the other end of the scale, if you have no data at all, there is a distribution wizard, which is basically there to help you make an educated guess about how you expect this failure to behave. Just use your own judgments to determine, do I expect to see wear out? Do I expect to see random failures? And in each case of the types of failure you expect to observe, you can just provide approximate information about what you expect. How long do you expect it will be before this thing starts to wear out? For example, how long before most of them have failed? From that, the program can build an approximate viable curve based on the information you provided. So whether you've got a list of times to failure, historical failure data, or you're starting pretty much from square one with no data at all, there should be a facility here to help you through that.
Okay.
Now, as well as failure, you can model repair and maintenance. That's done on the maintenance tab, where you can tell the program, on the corrective tab, how long does it take to fix this failure. You can even give the program information about the resources that you need to do that repair. This can include labor, equipment, so the tools essentially that you're using, and spare parts. Now, you don't have to include this information. It's a nice to have. It's something that you can provide if you have the data, because that will make your model more detailed and give you more granular results at the end. But if you don't have that information, it doesn't mean you can't use the software. It's just the more detail you can add, the more detail you'll get back. So if you want, you can add labor. If you've got labor in your project, or if you don't, you can add labor categories and basically tell the program, okay, on site, I've got 5 engineers. This is how much it costs to call them out. This is how long it takes them to arrive. You can fold that into your model then, and when the program does the simulation, all of that information is taken into account when predicting downtime and costs and other things. Same goes for equipment, tools you're using for the maintenance, and also for spares. So you can add spare parts to your project, tell the program how much a spare part costs. You can even include information about how many spares you can store locally and remotely, how much that will cost you, and how long it takes to get the spares out of storage. At level 3, you can even model the supplier. So with spare parts, you can almost make them as complex or as simple as you want them to be. You can just model how many spares you use and how much it costs to buy them, or you can do a detailed analysis of spare part storage, how much it's costing you. Should I store fewer or more spares on site or off site? So there's a lot of detail that you can have if you wish. So all of that information can be included as part of your analysis. You can also add scheduled maintenance as well. And this can be everything from planned maintenance and lubrication to fault finding and predictive inspection. So I could add a planned maintenance task, for example. Again, all the same things are here as you saw with the corrective maintenance, things like duration and resources. But now you can also specify how often this task takes place. So if this task represented a regular lubrication task, you can just say, I do this every month, and then provide the other information like how long it takes, how much it costs, click OK, and that will add that task to your failure model. And again, it works the same with inspection. It's just that now you can't have spares for an inspection, of course, and you also have the option to include predictive data. So if you want to do condition monitoring inspections, you can include P2F interval, detection probability. So if you, for example, were doing a vibration analysis of some bearings and you knew approximately how far in advance of a functional failure you could detect a problem and what the probability of detection is, you can include that here and model that inspection technique as well. And in the context of your simulation, as the program is analyzing the model, if a simulated failure is about to occur and the inspection picks it up, within the simulation, the PM will be triggered to prevent that failure. And there are other kinds of behavior that you can model as well, things like condition alarms, commissioning, redesign. Again, there's a huge amount of detail you can go into here if you want to, and if that data is available to you. So I can click OK, and there's my model. I can basically just drag and drop that onto any blocks that I want to use it. there are some useful viewing options where I can tell the program things like show the failure data under the block. So there I can now see the MTTF of those blocks. Maybe I can use the same model here as well. One of the nice things about the failure models is that if you've got lots of identical equipment in your system, you don't need to define the same MTTF over and over again. You can just create one failure model for that equipment and use it across all of those different equipment blocks. The blocks remain logically independent of each other. They just share the same failure behavior. And of course, if you go in and decide actually the MTTF on this guy is in fact 2 years instead of 1, that updates all the blocks that use that model.
Okay.
So we've looked there a little bit at, failure, repair, and maintenance, and we briefly mentioned some of the costs that we can include that are associated with those corrective and scheduled tasks. What we haven't looked at yet is the impact of the failure itself, so loss of production or regulatory fines for certain types of failure. That kind of behavior is modeled through the consequences. So you can have multiple consequences. I will add one here. Now, there are a couple of types of consequence. One is the total outage consequence, which will let you model basically the cost of a complete failure of a system. You can have a cost rate, like cost per hour while that failure continues, and you can have a cost per occurrence. So how much it costs each time there is a failure. So this might be good for modeling fines. This might be good for modeling the cost of lost production. Now, alternatively, there is the loss of capacity consequence. Now, AvSim is very good for modeling complete failure. So if you want to model an outage of a system, it's very good for that. It can also model degradation or partial losses from a system. So the system is still running, but maybe at only 50% of normal throughput. So I can have a loss of capacity consequence. I can say, how much it costs me for every percent of capacity I lose. What's my target capacity, and how much more do I lose if I fall below that target? I got that the wrong way around, but yeah, you can see what I mean when I say that.
Mm-hmm.
So I can click OK, and then for any block, or even for the system itself, I can attach that consequence. So I might open up the system and say, this consequence is associated with this system. So if my system loses capacity, I will incur the costs associated with that consequence. And for each block in my system, I can open that up and go to the Rules tab and tell the program, okay, this block on its own could handle 50%, and maybe this one can as well. So now, I can run at a full 100%, or if I lose one block, I can continue to run because there's still a path through my diagram, but it will be at a 50% level of production, and I will incur costs as a result.
Mm-hmm.
So we've talked a little there about the various different resources. There is one other thing that you can add here as well. These are called phases. They basically let you break the life of the system into different periods. So, you might have month 1, month 2, month 3, and so on. You might have week 1, week 2. You might even have day and night. The purpose of defining these phases is that for blocks and other objects in your project, there are these things called rules that allow you to modify the behavior of an object based on a variety of different inputs. Most commonly, phase. So for example, maybe the load factor is a good one. The load factor is a multiplying factor that modifies the failure rate of a block. I might say that during a certain phase, the load factor on this block goes up or down. So maybe during the nighttime phase, the load factor is 0.75 because I'm ramping down production slightly and there's a bit less stress on the equipment. There's even the option to modify some of these things by state, by the state of another block in the system. So I can say to the program, if this block fails, then my other block, its load factor will go up because I have to increase throughput on this block, and that's going to have a consequence that there is greater stress on that block as well, so it's more likely to fail. And these rules appear throughout the program. You can modify the behavior of blocks, consequences, maintenance tasks. There's all kinds of things you can do. This is really one of the more advanced features of AvSim. So there's one or two other things that are worth looking at, but maybe for the moment we can have a look at this simple analysis and see what happens. So before we do that, we can take a look at the project options. In here, I can tell the program what's the life of this system. I've set that to 10 years. I can tell the program maybe how many simulations I want to do. That's one of the key factors of doing a Monte Carlo simulation. The more times you simulate the life of this system, the more reliable the results of your analysis will be. It gives you better statistics to work from. I'll maybe do 1,000 simulations. And then maybe we'll take a look at importance. This is very useful because it will give you an idea of which blocks in your diagram are contributing the most to various different parameters, things like cost, downtime, and so on. So I'll turn that on, maybe run the analysis. So you can see it's working through that at the moment, so it should be done in a few seconds. And you can see that as it's doing more simulations, the statistical error is kind of going down. The more simulations it does, the better the result is effectively.
Okay.
So it's given me this cost breakdown to begin with. So you can see there, it's telling me how much it's costing me in terms of consequences, because I haven't really defined any other costs in this system as of yet. But as you can tell, if you can provide more detail, the program can give you a very detailed cost breakdown. Where those costs are coming from. You can get system availability data. So it's predicting in 10 years, I'm going to see about 1 month of downtime. What's the mean capacity? It's just under 99%. I can get availability data even for individual component blocks. And for my consequence, I can see, what's the mean capacity, what's the cost of that consequence. And I mentioned also that you can get importance data. There's a couple of ways to view that. The nicest one tends to be as a plot. So I can go to plot and maybe take a look at the contribution plot, and that's going to show me how much each of these blocks is contributing to various different drivers, things like cost or even downtime. I can switch that, so I'm looking at unavailability instead, and see where the unavailability or the downtime in my system is coming from.
Okay.
So maybe we'll take a look now at a slightly more detailed model. Maybe that one is a good one. So this is just like a kind of generic oil and gas kind of example where I've got some pumps in parallel, each one capable of supporting 50% of the throughput. You'll see I've got some kind of custom units here. That's something else you can do in the options, is change the equivalent of 100%. In my case, 100% is equal to 50,000 meters cubed per day.
Okay. So like for us, everything we would do from a simulation would be in pounds. How many pounds can we create on certain pieces of equipment, or so is that a possibility to input that as a unit of measure?
Yeah, so you can just basically do that through the simulation tab. So you can just change what equates to 100% to your own maximum and unit value. So if you if you're looking at pounds or megawatts or gallons or whatever it is you wanted to do, you could just put that in here. It's completely customizable.
Okay.
I've also got several layers of subsystems here. I'm modeling a buffer. Buffers are very useful. It's a special type of failure model that lets you model a temporary redundancy, where if there's a failure in your system, you can continue to operate for a finite period of time before the buffer is empty and the system goes out of service. So if you've got things like a redundant tank, or you're going to flare and you can only do it for a short period, you can model that kind of behavior. But probably the main thing I wanted to show here is that for the pumps and the valve, if I open up the failure model and have a look at the failure tab, you can see it's using a Bible set. So this is what I mentioned earlier on when I was talking about historical failure data. If I switch modules to the Bible module, here you can see I've got a couple of Bible data sets where I've imported a list of times to failure, which I've collected in the field. I could alternatively use work order dates if that's the format I have the data in. But the program, once I've imported that data, will automatically plot it on a cumulative probability plot like this one. And I can fit that data with a failure distribution. So you can see there's the line to fit to the data. There are the failure parameters that have been estimated from that fit. If I go back and say, look at the valve failure model, which is this one, you can see there's my valve set. There are the failure parameters estimated from that line fit. So the program is able to use the real world failures that we've observed to make our analysis more realistic. So we can run that analysis. Again, that's just going to go through maybe 1,000 simulations. We'll just take a few more seconds. And so we can run that and then take a look again, at the various costs that are coming through, system availability data, component availability data. In this case, you can see I now can see also spare usage and costs, labor costs and call out times and things like that.
How long is the so when it runs that simulation, it's simulating it for what time span? A year's worth of
so
runtime,
this one is being simulated over 20 years.
20 years. Oh, okay.
Yeah.
All right.
So yeah, this you can
over
set.
20 years, the information that it gives you is, I think it was like 139 hours of downtime or something like that.
That's right. So I guess that's probably about 2 weeks roughly of downtime for the system.
Over 20 years.
Yeah, that's right.
Okay.
And you can basically use that then. You can say go for plots, take a look at your contribution, and you can see, okay, well, my column flare is contributing a lot to downtime. It suggests maybe I need more redundancy in my column. So I can save that and maybe take a look at an alternative design. So I've got the same project, but now, maybe there is a different layout for my column. So I think maybe this is the wrong project. So I'm going to go and find the right one. So that's going to be probably in here somewhere. It's going to be up here. There. So in this one, so I think, so here's my column system again, but now maybe instead of having one big column, I've replaced it with 2 smaller redundant columns instead. So, I can run an analysis of that. And one of the nice things that AvSim allows you to do is compare the costs coming from 2 or more different versions of a project. So my intention here is going to be to compare this project to the previous one that we were just looking at and see how they compare with one another. One thing that is worth pointing out is if I look in the column failure model, I have included the cost of changing the system. So there is a redesign cost associated with that. So obviously I can't make this change for free. I'm going to include that as a redesign cost. So I'll save that. And I'm going to close those. Then I'll attach my original version of the project as a library. So let's find that now. That's in here. So there's the original version of my project. I've attached it as a library. Now, obviously, the main purpose of a library is it will let you drag and drop data between projects so you can share information from one project to another. The reason I'm using it here, though, is what I can do instead is I can go to plots and look at a project comparison plot. So this is showing the original version of the project as compared to the upgraded version of the project. So this project is the one that has 2 small columns instead of 1 big one. That big red block here is my redesign cost, but I can see that my consequence cost has dropped enough that that's being absorbed, and I'm still saving money by doing this instead of having 1 big column. So I can use that to kind of justify the expense of changing over from one system to another. I can even see how that sort of pans out across the years. I can modify the plot options and say, I want to look at a cumulative cost profile. I won't stack the plot. And that's basically comparing these 2 versions of the system over years. And you can see at first, the upgraded project is of course more expensive, but as we approach the halfway point, we actually start saving money rather than being out of pocket. So you can actually see there not just how much money you might save, but when those savings will start to come into effect, essentially.
Yeah, interesting.
And I've done that with just 2 projects. You could do it with 3 or 4 or more. Obviously, a plot like this is going to get quite difficult once you start having 10 projects, but obviously you're not limited to just 2. So that's an overview of AvSim itself. I will show you some of the reporting facilities as well. But before we look at that, do you have any questions about what we've seen so far?
No, I'll be honest with you. I'm kind of blown away on how detailed you can really get with it. It's pretty cool. It's very cool.
Very good. That's good to hear.
Yeah, I wasn't expecting to be able to input that much data into it. But I think it's pretty neat. I mean, I don't know if we're there. I know we've talked about simulating certain things. It's interesting to know that there's softwares, and I knew there were some softwares out there. I didn't know which ones, but I knew it's good to know that there's softwares out there that we can simulate certain layouts of our lines. We have talked about that and redundancy in certain areas. It's just that we haven't really sat down and said, okay, yeah, that redundancy, if we put it in here, is going to equate to X amount of availability and or more pounds, out of that line. So, okay. And I think this stuff can definitely do that.
Excellent. Well, I mean, with the results that come out of AvSim, naturally, you're going to want to show that in the form of documents that you can hand to people who don't necessarily have access to the software themselves. The program does have integrated reporting facilities. So the way that works is that you can open a report template file, and that template will automatically populate with data from your current project. And those templates are all customizable, and you can create your own as well. So if I show you some examples, maybe I'll open a report and we'll take a look at some AvSim predictions and system availability. Let's see if that one's working. Yeah, so there I get a list of my systems with some basic availability data alongside them. Now, of course, you can add columns to this or remove them. If you go into design mode, you can do all kinds of things. You can filter and sort on the columns. You can even modify the underlying query that gives you these results. Create your own highly customized report. I won't go into a huge amount of detail here, just to say it is based on an underlying SQL query. So if you wanted to do something super custom, quite advanced, but you weren't sure how to approach it yourself, this is something we very frequently help with through our technical support agreements. So you come to us and say, I need a report that shows X, Y, and Z. Can you help me to build it? Usually it's not too difficult for us to help out with that.
Yeah.
And so if I go back to reading mode, and that's not the only kind of report you can show. There are, of course, graphs, plot reports, so block cost importance, a bit like the ones we were looking at earlier. Just a bar chart showing you which blocks contribute the most. People sometimes like to view this as a pie chart. You can change this to a pie chart in the design mode as well.
Okay.
And of course, the main report probably is going to be the block diagram itself. So you can open a diagram report, and there's my block diagram with each subsequent page showing a different subsystem of my diagram. And of course, all of these reports you can print. They can also be published in Microsoft Word and in PDF. And with the text reports like this one, you do have the option to export to a text file. Things like CSV and tab delimited files, you can even open in Excel if you wanted to.
Yeah.
So there's a lot of reporting options there as well. Did you have any specific concerns about reporting?
No, I mean, it's just interesting. It's just good to know that obviously you can, summarize all of it. You can give that to some executive leadership that, wondering about some of this information. So it's a nice way to summarize it.
Okay, excellent. So I guess the last thing to mention then is just that, if I guess it's quite possible you've got bills of materials and that sort of thing in Excel or other formats. The program has pretty powerful import and export facilities as well. So if you go to the file menu, and you can see import and export there. If I click on import, and you can see there all the formats we support for import of data.
Okay.
In principle, it's possible to completely construct and deconstruct a project from, say, an Excel spreadsheet file. So you could build your diagram even from it if you were feeling brave. Usually that's not a practical thing to try and do anyway. But of course, if you have MTTF data, if you have lists of spares and their purchase costs, those sorts of things, the kind of things you need just maybe to get started building your project, you can pull them in and just save yourself the sort of error-prone, tedious job of entering the data all by hand.
Okay.